Hi, I'm Conor Houghton, and this is lecture 1 in the Bayesian Brain section of our unit, Information Processing in the Brain. This lecture is just intended as a quick reminder of Bayes' rule and a quick outline of the so-called Bayesian approach to studying the brain. Lectures of this sort, by tradition, start by showing this xkcd cartoon and then over-explaining it and ruining any joke that there might have been there to start with. In this cartoon you have two people and they're wondering if the sun has just exploded. So it's nighttime, so they can't just look out of the window or up at the sky or whatever, and instead they're using a neutrino detector. So a neutrino detector, neutrinos can travel through the earth, they don't interact. There's even a poem by John Updike about it called Cosmic Gold that starts, neutrinos, they are very small, they have no charge and have no mass, and do not interact at all. The earth is just a silly ball to them through which they simply pass. And then it goes on. But of course, just to show that I don't understand how jokes work, the fact that they can travel to the earth means that it's actually very hard for the detector to detect them, and a detector of this sort, the neutrinos would just pass through it as well. It would be unable to detect the neutrinos, and if it did, it would only do so very noisily. For the purpose of this joke, though, so-called, the neutrino detector reliably detects the neutrinos, but then it does this weird thing, which is, so you ask it, has the sun exploded? It checks whether there's neutrinos passing through it, consistent with a nova. It measures them, decides accurately, with complete accuracy, whether or not the sun has exploded, and then it answers yes or no. But before it answers, it rolls two dice, and if the dice both come up sixes, it lies. And so one time in 36, when the sun has gone into a supernova, it will into a nova rather, and when the sun has exploded, it will say no, even though the answer should be yes. And one time in 36, if the sun has not gone into a supernova, it will answer yes, even though it should say no. So these two people, they have decided to check. They've pressed the button to ask the machine, has the sun exploded? And the machine says, yes. Oh my God, the sun's exploded. That's precisely the reaction of the person on the left. So the person on the left is supposed to be a frequentist, and they reason as follows. The probability that this result happened by chance is 1 in 36. That's less than the magic number of 5%, that is the traditional threshold in frequentist statistics for taking statistical results seriously or believing it to be true, and hence the frequentist, notwithstanding the fact that the machine does sometimes work slightly randomly, the frequentist concludes that the sun has exploded. The Bayesian doesn't think so and bets $50. So of course there's another joke, which is that they won't have to pay the $50 if the sun has exploded. But leaving that aside, the reason they bet $50 is that they don't believe the sun has exploded, notwithstanding the reaction of the machine. And we all know why that is. It's because the frequentist is only taking into account the behavior of the machine, the probabilities associated with the detector, and not taking into account the probabilities associated with the basic event, the event that the sun has exploded. So we're going to quickly do the calculation and explain why the Bayesian might be right, and before doing that we'll just recall Bayes' rule. So Bayes' rule is reasonably straightforward. If you remember, the joint probability, the probability that x happens and y happens, is equal to the probability that y happens and the probability multiplied by the probability that x happens if y has happened. That's more or less the definition of the conditional probability. So px comma y is equal to px given y multiplied by py, but px comma y is symmetric in x and y, and you could do the logic the same way. The probability that x and y happens is the probability that x happens multiplied by the probability that y happens given that x has happened. And so px comma y is also equal to py given x multiplied by px. You set the two things that are equal to px comma y equal to each other, divide across by the py, and you get Bayes' rule. So Bayes' rule is a simple deduction from the definition of the conditional probability, and you wouldn't think that such a basic and undisputed rule of statistics would be controversial and would have communities called Bayesians and another community which, for the purposes of this cartoon and sort of jokes in the mathematical and statistical community, are the opponents, the lifelong clan-like opponents of the Bayesians. But what has happened is that this rule plays a different role in the Bayesian interpretation of statistics to the role it plays in the frequentist approach, or it plays a more preeminent role in Bayesian interpretations. So obviously the rule is correct, and probability theory is mathematics. And so these communities are not divided on the truth or otherwise of Bayes' rule. They're divided on what it is that they are modelling with probability theory. So I'll talk a little bit more about that in a minute. For now, let's go into tedious detail through the calculation underpinning what was originally intended to be a joke by Randall Munro, the author of the XKCD, the webcomic. So just to put some maths on it, D is the state of the detector. So D is a random variable with two possible states. W is the state corresponding to the warning, and then another state corresponding to not a warning. And so whenever you draw from D, you get a W or whatever this other letter is. D is what's happened in the cartoon. Similarly, S is the state of the sun. The sun, for these purposes, has two possible states, N, which is when it's exploded, and F, if it continues to be fine. So again, S is a random variable. The sample space has two elements. So from the cartoon, we know that if the sun is still fine, S equals F, then the probability that the detector will issue a warning is 1 in 36. It only does that on the occasions when it doesn't tell the truth, when the detector lies, and that's what happens when it rolls two sixes. And so this number here is close to 0, so the probability that it gives a warning when the sun is fine is 1 over 36, and so this is what prompts the frequentist to believe that the sun has exploded. However, let's discuss the explosion of the sun in the context of assigning an overall probability to that event. So here again, the probability that the detector gives a warning if the sun has exploded is 35 over 36. What's the probability that the sun has exploded? Well, that's not described in the cartoon, and that's something we have to decide ourselves based on the evidence. I've assigned a number here of 10 to the minus 6. That's clearly much too large. I don't know why I didn't say 10 to the minus 50 or something, but the sun, we know from previous experience, for the fact it hasn't exploded for the last 4.5 billion years, it is unlikely to explode in any given year, yet alone in any given at any given moment, and so that raises the question: should this be a continuous or a discrete probability? But we're assuming that you press the button on this machine at most once every few minutes, and so there's a very small chance of the sun exploding, and I've represented that by saying assigning a probability of 10 to the minus 6 to it. So that's the underlying a priori probability that the sun has exploded. That's the probability we assign to the sun having exploded before we do anything further to gather more evidence about whether or not the sun has exploded. And gathering more evidence is precisely what's happened. We've pressed the button on the neutrino detector and it's told us that the sun has exploded. And so we do have more evidence as to the state of the sun. We have the evidence of the neutrino detector, and that has clearly told us the sun has exploded. And so we need to reassess the probability that the sun has exploded. So before we had assigned 10 to the minus 6 to the probability the sun has exploded, now we're looking to see what our new probability is. And so for some reason I've switched these around, and now I'm going to work out the probability that the sun is fine given that the detector has given a warning. So obviously the thing I just described, the probability that the sun has exploded given the detector has given a warning, will be 1 minus whatever we calculate here. And then we use Bayes' rule. And the thing that Bayes' rule often ends up doing, certainly in examples like this, is it turns the order of a conditional probability. I mean, mechanistically, that's what we use it for in analysing data, and certainly in the sort of problems that are treated by Bayesian statistics. So here we have the probability that the detector gives a warning given that the sun is fine. That's something we know. That we can assess. That's basically a measure of the noise in the machine. The probability that the sun is still fine, that's the thing that we're interested in. Is the sun still fine? In this picture, we already have some idea about whether the sun is still fine or not. We have an a priori probability, which will be 1 minus 10 to the minus 6. And we also have some model of the machine. How often does the machine give this warning, the warning that the sun has exploded? So let's deal with these different terms. The numerator is easy, as I said before. This is the thing that is described in the cartoon, the probability the detector gives a warning if the sun is fine. This is the thing we've already discussed, giving a probability to. It's 1 minus 10 to the minus 6. The bottom, the denominator is no harder in this case to calculate. Sometimes denominators are hard to calculate. In this case, we can do it. We just have to marginalize various distributions. So the probability that the detector gives a warning, well, there's two cases where the detector gives a warning. One where the sun has nova and the other where the sun is fine. And these two probabilities we can work out by re-expressing them in the way that we discussed before as conditional probabilities. So the probability the detector gives a warning and the sun has exploded is the probability that the sun has exploded multiplied by the probability of the detector giving a warning given that the sun has exploded. And this is the same but with the sun being fine. And in fact, those two terms are identical. So we can easily work out the denominator, we can easily work out the numerator, we can shove the figures in, and what it tells us is that the probability the sun is fine is 0.999965. So even though the detector is given a warning, notwithstanding the warning from the detector, and notwithstanding the fact that considered in isolation, the detector has quite a low rate of noise. But the low rate of noise in the low rate of unreliability in the detector is huge compared to the overall unlikeliness of the sun having exploded. And the fact there's only 4 nines here, as I said before, is because I've only assigned a chance of 1 in a million that the sun has exploded, when I believe that chance is much smaller still. So that's basically just an application of the Bayes' rule. So there's nothing controversial about that. In the cartoon, we had two different people interpreting the event of the detector beeping in different ways. One is a frequentist, one is a Bayesian. In the cartoon, the frequentist is the chump. They've made a mistake. Clearly, they shouldn't think that the sun has exploded because they haven't taken into account, as we described, the overall improbability of that event. And in fact, of course, frequentist statistics is a very sophisticated, very complex piece of mathematical infrastructure machinery that's been developed over the last 150 years or so, that allows us to perform all sorts of useful, vital, important calculations on data, on measured data from the world. And so, we shouldn't run down frequentist statistics. As I said, they didn't do it out of naivety. They did it to solve a particular set of problems, and they have achieved an awful lot. I mean, statistics has achieved an awful lot in solving these problems. Bayesian statistics is a different approach or a different way of modeling problems with statistics, subtly different. It's not vastly different, subtly different, and it's appropriate maybe for slightly different problems. In fact, the sort of problems that the brain has to solve. So a creature has to make decisions about the state of the world in order to then act in an ecological way. The creatures are always trying to eat, access opportunities to reproduce, and avoid predation from other creatures, or just accidents being stood on, or whatever. So animals are trying to understand what the world is like, so they can use that for the basis of behavior. If they understand the state of the world, they can assess potential changes to that state according to the way that they behave, and they can assign value to the different choices and choose the one that's best for them. And maybe the problems animals solve are very complicated. Maybe in some situations they have to make choices quickly, and they use very quick calculations. Other times they have more time to make the decisions. But the central thing is that the animal is taking in information about the world through ears, eyes, etc., through the sensory system, proprioception. It's also making assessments based on its previous experience of particular actions. All of these are uncertain. So it has a model of the world, an internal model of the world, which it uses to assess the current state of the world, bearing in mind different pieces of overlapping evidence that come with some estimate of the uncertainty of those elements, of that evidence, and it uses that to decide to make an estimate, again, coming along with an estimate of the uncertainty, to make an estimate of the current state of the world. That's what the brain does, and that's basically a Bayesian calculation. And in the next lecture, we'll see a very particular example of that has been used as the basis of a psychophysical experiment. So again, just to finally recap, the laws of probability are mathematics. They are true and immutable in the way that mathematics is. You have a set of objects which you define. You have the sample space, in the simplest case a discrete sample space, and probabilities on top of those possible outcomes. And the probabilities have to obey some rule. They have to be positive. They have to add to 1. And so that in and of itself is just a piece of mathematical definition. You define things on top of it, like the conditional probabilities. You go from the original probabilities and the outcome to probabilities and events, and so on. You build up some mathematical structure. That is beyond argument in the way that mathematics often is. But it doesn't determine what exactly you're modeling. So it doesn't determine what you mean by P, what the probability is, it means, and in turn it doesn't determine what it is that you want to do with these probabilities. And so sort of frequentist school of statistics and the Bayesian school of statistics differ only in what problems they're attempting to solve, and in a subtle way on how they interpret in probabilities. And this is illustrated here. I took this figure from Rosalind Moran, who taught an earlier version of this course probably 4 years ago. In this picture, we have on the left a sort of frequentist view of what a probability distribution does, and on the right Bayesian. So again, it isn't that one of these two views is correct. It's just these are different ways of employing the machinery of probability to model some situation and to use again statistics and probability to do something useful with the situation. So in the left, the probability is a distribution modeling the random behavior of something. So it's the Geiger counter, the flipping of coins, the randomly opening a book and picking out a word. That is a random event that we're going to experience many times. So we have the random variable x modeling this experiment or event, and we'll do many trials and we'll draw many values x out of that probability. And so what we'll end up with is lots of data, the distribution of which is determined by this probability distribution. In the Bayesian case, we would generally have one event. The animal is just looking at the world at the moment and trying to assess what the world is like. And so they're not going to be drawing many times from the random variable. Instead, what they want P to do is to model the noise or the uncertainty in their assessment of the state. And so in the frequentist case, you have the probability distribution and you draw many times from it. In the Bayesian case, the probability distribution represents your uncertainty about the value x that you have in mind. So you have, on the right hand side, you have the probability distribution is modeling your knowledge or your ignorance. Let's do a quick sort of illustrative example. Hopefully this is helpful. Imagine that the experiment that we have in mind is that somebody opens a book, chooses a book at random from a bookshelf, and they open a page. In fact, they open the first page and read out the first sentence, but they leave off the last letter. And you're asked, what is the last letter? So maybe you're going to bet on what the last letter is, and maybe the person is offering some reward if you make the bet correctly. And so, you want to, the sentence is already chosen. You're not going to be able to do many trials. This is why this is subtle. What you can think of this is, what would happen if I did many trials? And you would come up with your assessments of the probability distribution by thinking about what would happen under a multi-trial scenario. But for you, as it stands, the selection has already been made. There's a single unknown letter, and you want to guess what that letter is, but also make some assessment as to how likely your guess is to be correct, because that will determine whether you take the person's bet or not. So the person says, listen, you give me £1, guess the letter, and if you get it correct, I'll give you £2. Now you have to work out, is that a worthwhile thing to do? So you want to not only make a guess, but come to some determination about the probability that your guess is correct. Obviously, in this case, a person doing this who has who looks at this and reads "Call me Ishmael" will guess that the last letter is L, because they know that this is the first sentence of Moby Dick, the book about this ferocious sperm whale. But imagine that you don't know that. So you're a computer, or you just haven't heard of Moby Dick, and you want to play this game. And so you want to guess what the next letter is, and you want not only to guess what the next letter is, but you're being offered a bet. You want to try and work out whether it's worth taking the bet. You want to work out how certain you are. Again, this is like what animals do. They have to expend some energy to try and access some food source. They have to take some risk of predation to access some opportunity for reproduction. Do they do it? Well, they assess the probabilities. They assess the uncertainty of their knowledge or their belief in what might happen if they try to do whatever it is they think they're doing. So in this case here, the simplest thing you could do would be to say, well, how probable are different letters? If I just choose a letter at random from a corpus of text, how probable are they? And here from Wikipedia, we have actually a representation of letter frequencies in English text. And so they'd say, well, the most likely letter it is an E, but even in that case, I'm only likely to be right with probability 0.13, because 13% of letters chosen at random from an English text will be an E. L is 4%, Q, for example, is 0.1%. And so here we have a probability distribution over the letters. We've taken the probability distribution from thinking about an experiment where you just open a text at random and pick a letter at random. So it's not like we're divorced from this more frequentist approach. But in our particular situation, we're not doing multiple experiments, but based on our knowledge of our model of what might happen, we assign a probability to different outcomes. Now, obviously, there's better ways of doing it, and the better way to do it would be to look not at individual letters, but to look at the n-gram. Surprisingly, this doesn't actually change anything very much, but what you would do here is you would ask, given that the letter before it is E, what is the probability distribution of this letter? So what you'd be looking at is you'd be looking at all the two-letter pairs, ER, EL, EQ, and so on. Actually, what does change is that EE is pretty unlikely. So I look at all the pairs, I do some study of English, I work out, given that the first letter is an E, so given that we have this E here, how likely is the next letter to be L? And that would be the probability we now associate with L here. So these are the probabilities of the outcome of the experiment. This conditional probabilities are what we use to make these estimates. And so here now we come up again with some guesses and some assignment as to the probability of those guesses being right. So as I said, previously we had PE here. This time the highest probability, the most likely result is that it's an R. Call me Ishmael. Obviously ERs occur a lot, later, better, etc. And so we might, if we were to take the most likely letter, guess it was an R, and we'd know that we were right with a certainty of 0.14. So our probability, our certainty, is the same as it was before, but the actual probabilities we assign to different letters is different. And you'll notice that the probability of L stayed the same. That's just coincidence. The probability of Q has gone down quite a bit. So so now we have a different probability distribution. But the thing to I'm trying to point out here is that nothing has changed. The person who's playing the game with us hasn't changed the likelihood of different letters being the next letter. The next letter is going to be L. That's basically the answer. That's the next letter in this opening sentence, call me Ishmael. All that's changed is our knowledge. So we've come up with a better model for what the next letter might be, and that's changed the probabilities we've assigned to it. And so we see here that the probabilities are a measure of our knowledge or our ignorance of what the next letter might be according to our model of what the next letter might be. And if we go up to the 3 gram, in fact, we can see that the correct letter is actually winning out here quite dramatically. So now we've looked at what the probability of different letters following AE, and we'll find that R actually now occurs only 0.1 of the time, so P of R is 0.1, P of L is 0.4, so 40% of times when you have A in English, the next letter is L, like I guess Raphael, Ishmael, I can't think of any others off the top of my head. P is just another random example, so 0.1% of the time that you have AE, the next letter is P. But again, the main point is that I have now got a better model. I've added more information, in fact, to my attempt to perform inference, into my attempt to decide or guess what the next letter is. So initially I wasn't looking at anything, I just knew I was choosing a letter. Then I was looking at the previous letter being E. Now I'm looking at the previous letter being the previous letters being A followed by E. So in each of these steps, I've kind of I've changed my view as to what the next letter might be, or the probability of what of different letters filling the asterisk spot, because I've added more information to my estimate. And you might go on and look at more letters or do something more sophisticated, like you know, an LSTM or something, and none of that will actually change the answer. The answer is always going to be L, but what it will change is the probabilities we assign to the different possible results. So that's more or less all I have to say. To summarize again, the problem the brain faces is a Bayesian one. We gather information about the world through our senses. These are unreliable and limited, but we still have to make some inferences to the state of the world, and we do that based on the information we have and on our ability to update the information we have when we get more information, or in the case of active inference, by actually making some decision as to what information we should gather in order to get the best or most informative update. And so this kind of describes the Bayesian interpretation of Bayes' rule. So Bayes' rule, as I said, is mathematics, but the Bayesians have a way of interpreting it that is pertinent to many of the things that they're trying to do in, for example, modeling inference in animals. So in Bayes' rule, here W is supposed to represent the state of the world, and E is supposed to represent some evidence. And so in this equation, we have some idea of the state of the world. So we've attributed some probability distribution to possible states of the world. The value of the letter covered by the star in the example we're just looking, but other more complicated things to do with which lever will give us a food, or which lever in a gambling machine or which gambling machine is likely to give us a payout, or whatever. So this is our understanding of the world, and this is what we call the prior. It's our model of what the world looks like. It's the probabilities we associate with different possible states of the world before our new piece of evidence. Now there's a new piece of evidence, and we can maybe make some estimate or even calculate how likely that evidence is given the state of the world. So this P of A given W is is what's called the likelihood. It is we have some evidence, or we're going to do an experiment, and we can ask what is the likelihood, how probable are different pieces of evidence given the state of the world. Here is a model of what the evidence looks like. How likely, quite apart from the state of the world, so averaging over all possible states of the world, how likely is the evidence? This is often a thing that's quite hard to work out, although you should be able to get it by summing terms that look like the numerator over all possible values of W. So taking all that into account, we now have a new model of the world. So now we can condition, so we're imagining we do the experiment, we find out the value of E, the evidence, and we ask what is the probable state of the world given that we now know the result of the experiment. So the result of the experiment in the previous example might be looking at what the previous letter is, or the letter before that. That will allow us to update the state of the world. And so this is now our model for what the world looks after we have the piece of evidence, after we've done the experiment. And so that's referred to as the posterior. Posterior meaning behind, obviously, but in this context, afterwards. So we have the prior, we have some evidence, we can work out how likely the evidence is given the state of the world, and we can use that then to calculate, to come up with a new a model of the world, so a new set of probabilities assigned to different possible states of the world, and we call that the posterior. And so the act of Bayesian inference in trying to understand the world, what we think the animal brain does in a Bayesian model of the world is it repeatedly updates the state of the world, so it calculates a posterior based on evidence. So there's sensory evidence coming in, etc., etc., etc. It uses that evidence to update its prior belief about the world to give it a new belief about the world, where by a belief about the world we mean the assignment of probabilities to potential states of the world. And then that posterior will then become the prior for the next experiment. So what we should, maybe I should have drawn a circular arrow here, where the prior is what we believe the world to be after the previous piece of evidence. That's all in the past now, so now this is our model of the world. We then get the new piece of evidence. We use the Bayes' rule to calculate the posterior. That posterior then becomes the prior when the animal looks for further evidence. And this text here just describes that. So that's the Bayesian brain. Like I say, in the next lecture we're going to see a particular example where we can see that that's in operation. Thank you.